Hello everyone, welcome to OHM Institute. I am Surendra Reddy, faculty for electrical machines. So in this lecture, I am going to continue the series on previous gate examination questions. The subject is electrical machines. That too, the topic is DC machines. I have completed already part 1 of this lecture, and this is going to be part 2. So in part 1, we discussed the questions up to gate 2015, and now we will resume our lecture and we will try to answer the remaining questions as well. Okay. So the first lecture of today's lecture, video is from gate 2015. Okay. This is from gate 2015. So let's read the problem. A separately excited DC motor runs at 1000 RPM on no load when its armature terminals are connected to a 200 volt DC source and rated voltage is applied to the field winding. The armature resistance of this motor is 1 ohm. The no load armature current is negligible. With the motor developing its full load torque, the armature voltage is set so that the rotor speed is 500 RPM. When the load torque is reduced to 50% of full load value under the same armature voltage conditions, the speed rises to 520 RPM. Neglecting the rotational losses, what is the full load armature current in ampere is the question. Okay, so this is an important question. It's a 2 marks problem, and here 3 cases are there overall. If you read the problem, let's see the first case. A separately excited DC motor runs at 1000 RPM on no load. See, the first case is no load condition. When its armature terminals are connected to 200 volt DC source. So the supply voltage was 200 volt. And rated voltage is applied to field winding. Okay. Armature resistance of the motor is 1 ohm. Now the no load armature current is negligible. Okay. This is the first case, guys, up to here. So up to here, whatever is mentioned, that is no load data of the machine. Now let's continue. With the motor developing its full load torque, this time full load condition is discussed and the armature voltage is set. This indicates armature voltage changes. Okay. Armature voltage is set so that the rotor is rotating at 500 RPM. Okay. This is going to be the second case. I will use a different color. See that from here. With the motor developing its full load torque. So second case is full load torque. Armature voltage is modified so that rotor is rotating at 500 RPM. So this is the second case, indirectly full load torque condition. Now the third case will start here. You see that. What is the third case? Yes. When the load torque is reduced to 50%. See, clear information. This time the torque is reduced to 50%. That is half load torque condition. Okay. 50% of full load value under the same armature voltage. That means whatever voltage we used in the second case, same voltage is continued. Okay, the speed is raised to 520 RPM. This is going to be the second case, a third case, guys. That is half load torque condition. Now the speed is raised to 520 RPM. Okay. Now, neglecting the rotational losses of the machine, what is the full load armature current drawn by the motor? So, first what I will do is that I will take case number 1, that is no load condition. Case number 1, which is nothing but no load data. It's a 2 marks question and important model as well. And most important observation is machine is separately excited, therefore field flux will be a constant value. So, what is the supply voltage in the first case? I will write it as VT1, which is equal to 200 volt, clearly mentioned, supply voltage 200. No load armature current is neglected. We know armature current drawn by under no load condition is very small. That can be neglected because rotational losses are neglected, right? That's why no load armature current is neglected. And what is the speed at which the machine is rotating? 1000 RPM. The rotor speed is equal to 1000 RPM. Now immediately we will try to calculate back EMF of the motor. What is the formula for back EMF? There are 2 formulas for back EMF. One is KVL equation, another one is performance equation. So if I use KVL equation, back EMF is equal to VT minus IA into RA. But as no load armature current is 0, IA RA drop is neglected. Therefore, back EMF value is equal to simply Vt. What is the magnitude of Vt right now? 200 volt. That means the first case back EMF is also equal to 200 volt. I got a back EMF in the first case. Okay. And I have one more equation for back EMF, which is performance equation that I can use later. Now this is a no load condition is completed. Let's move to full load condition. That is the second case. See, with the motor developing full load torque, this is the second case. Armature voltage is set. Armature voltage is set means it is modified. I don't know what is the modified voltage, but it is set such that the machine speed is reduced to 500 rpm. Okay, so case number 2 now. Case number 2, how much torque is connected? Full load torque. Full load torque. Okay, so voltage is also modified. Voltage is set such that machine will rotate at 500 rpm. So I don't know what is that new voltage. Let us say VT2. I don't know this value. As a load is connected, machine will definitely draw some current. We don't know what is that current. In fact, this is the answer we need. What is the answer? Finally, we are asked to find out what is the armature current drawn at full load. That is the answer we need. That means indirectly, this IA2 is the answer we need. How much torque is connected, guys? Full load torque. This is a second case. Everything is suffix number 2 because it is a second case. And machine is rotating at how much speed? 500 rpm. Okay. So calculate what is the back EMF of the motor. So I have KVL equation. EB2 is equal to VT2 minus IA2 into RA. I don't know what is the back EMF. I don't know VT. I don't know IA. Nothing is known in this equation. Therefore, I will go to performance equation. What is the performance equation for back EMF? EB is equal to Ka phi into omega. This equation we know. And here, flux is a constant value since the machine is separately excited. Therefore, back EMF will be proportional to only speed. If back EMF is only proportional to speed, can I write EB1 divided by EB2 is equal to N1 divided by N2? Simple. What is EB1? That is the first case back EMF. We already calculated. First case the back EMF is 200 volt. So I can use that. 200 minus second case back EMF we don't know is equal to first case, that is a no load speed. How much? 1000 rpm. But now at full load the speed is 500 rpm. 500 rpm. So can I say solving this I will get EB2 is equal to exactly half of 200, that is 100 volt. So I can substitute. So EB2 is equal to 100. I don't know what is VT2. I don't know what is the armature current, but armature resistance is given in the problem, right? Yes. What is the armature resistance? You can see here, armature resistance is 1 ohm. So I know armature resistance is 1 ohm. That means indirectly 100 is equal to simply VT2 minus IA2. You can understand there are two unknowns available here. Okay. If I find one more equation with the same two unknowns, I can solve both of them so that I can get the answer for the current drawn by the motor. So to get that, we will move to the next case. What is the next case? Half load torque condition. See that? When the load torque is reduced to 50% of the full load, that means the torque is reduced to half. Okay, 50% of full load value. Under the same armature voltage conditions, it is very clearly mentioned voltage does not modify. That means whatever voltage I used in the second case, that is a full load torque case, same voltage I have to use again. Okay, so case number 3. Case number 3. This is half load torque condition. Half load torque condition. Okay, so therefore that is T3. T3 is equal to half of T2. Voltage is the same maintained, right? So third case voltage is the same as second case voltage. Okay. But what is the speed now? The speed was raised to 520 rpm. It was very clearly mentioned. The speed is raised to 520 rpm. So using this new speed, I can calculate what is the new back EMF. What is the formula for back EMF? EB is equal to Ka phi into omega. As the machine is separately excited, flux is constant. So back EMF is only proportional to speed. So I can write EB2 divided by EB3 is equal to N2 divided by N3, or EB1 divided by EB3 is equal to N1 by N3. Any formula you can use. What is back EMF in the second case? 100 we already calculated. What is the back EMF in the third case? We don't know. Speed in the second case 500 RPM. Speed in the third case 520 RPM. Clearly mentioned in the problem. So you will get what is the back EMF in the third case, right? So if I solve it, 520 divided by 500 into 100. So 104 volt. This is going to be the back EMF in the third case. And I got this back EMF using what? Performance equation. So I can use one more equation, that is KVL equation. What is the KVL equation for third case back EMF? EB3 is equal to VT3 minus IA3 into RA. EB3 we got 104. But tell me one thing, VT3, VT2 both are same, right? Voltage is the same maintained. Therefore, I can write VT2 minus IA3, I don't know. That is the third case armature current, I don't know. But resistance I know. So, 104 is equal to VT2 minus IA3. So, this is the other equation we got. What is the previous equation we got? In terms of VT2, IA2. But the present equation is in terms of VT2 and IA3. Therefore, if I find a relation between IA2 and IA3, I can solve this problem. How to find out the relation between IA2 and IA3? That is second case armature current and third case armature current. Yes, that is where you can use the torque information. In the second case, how much torque is connected? Full load torque. Am I right? But in the third case, half load torque is connected. So therefore, use that torque information now. We know what is the torque equation? Ka phi into Ia. Yes or not? This is a standard torque equation. But here flux is a constant value because machine is separately excited. Therefore, torque is proportional to Ia. That means T2 divided by T3 is equal to Ia2 divided by Ia3. We need the relation between Ia2 and Ia3. So what is T2? Full load torque. What is T3? Half load torque, that is half of full load, is equal to Ia2 divided by Ia3. So from this, Ia3 will be equal to half of Ia2. Okay, Ia3 is equal to 0.5 times of Ia2. Now what you can do? You can use this Ia3 value in this equation now. Therefore, what will be this equation now? Yes, I will change the color. Therefore, 104 is equal to VT2 minus, what is Ia3? 0.5 Ia2. This is the new equation we got. Let us say this is equation number 2. Already we got equation number 1. This is equation number 1. So see, this equation is in terms of VT2 and Ia2. Even the next equation also in terms of VT2 and Ia2. I can solve both equations now. Okay, so note down this equation. And what is the next equation we have? 104 equation. So if I solve both of them, I will note down here. Yes. What is the first equation we got? 100 is equal to VT2 minus Ia2. But 104 is equal to VT2 minus 0.5 Ia2. Now solve these two equations. You will get answer for VT2 as well as Ia2. Isn't it? But what is the answer we need? Sorry, VT2 must be volt, right? This must be volt. Okay. What is the answer we need? The ultimate answer that we need is what is the armature current drawn at full load? Full load means second case. Okay. Ia2 is the answer we need. So solve both of them. You will get the answer for VT2 and Ia2. Let me do it. So I am getting the voltage as 108 volt and current as 8 amperes. Therefore, our ultimate answer is 8 amperes. That is the armature current drawn at full load condition. Okay, so it's an important model because three cases are involved. First no load case, but next to full load and then next to half load. But in full load case, voltage is modified and the same voltage is maintained at half load as well. Okay, yes, the answer is 8 ampere. All right, let's move to the next problem. This is a question from GATE 2015. Read the problem. With an armature voltage of 100 volt and rated field winding voltage, the speed of a separately excited DC motor driving a fan is 1000 RPM and its armature current is 10 ampere. The armature resistance is 1 ohm. the load torque of the fan is directly proportional to square of the rotor speed. Neglecting rotational losses, the value of armature voltage which will reduce the fan speed to 500 rpm is dash. Once again, the question is from DC motors. First understand, initially what is the armature voltage? 100 voltage is used. Rated field winding voltage, that is important. The speed of a separately excited DC motor. The question is from a separately excited DC motor is 1000 rpm. Okay, initially 100 voltage is used, speed is 1000 rpm. Armature current is also given, armature resistance is also given. Now the load torque of the fan, this is important, the load torque of the fan is proportional to square of the rotor speed. This is the given information. Now the value of armature voltage is modified. The armature voltage is modified such that the speed of the fan is reduced to 500 rpm. What is that new voltage? We have to calculate. So there are two cases here. In the first case, machine is excited from 100 volt and rotating at 1000 rpm. So in the second case, what is the voltage required? You have to modify the voltage such that speed reduces to 500 rpm. So first let me note down case number 1 details. In case number 1, what is the voltage applied to motor? It is 100 volt. And what is the armature current drawn by the motor? 10 ampere, isn't it? And what is the speed at which the machine was rotating? 1000 rpm. These are the details about the first case. Now calculate back EMF of the motor. Yes, what is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra. See, for Vt also I am writing suffix number because voltage is modifying in this question. Yes, what is the voltage? 100 minus armature current is 10 ampere. And what is armature resistance? 1 ohm. Therefore, back EMF is equal to 90 volt. This is the first case. I got the back EMF value. Let's move to the next case. In the next case, what was happened? Case number 2. Voltage is modified. Definitely, voltage is modified. That is the given information. So that the speed of the motor reduces to 500 rpm. So, what is this voltage must be? So, you have to calculate what is the new back EMF here. If I calculate new back EMF, I can easily find out what is the new voltage required. But to calculate a new back EMF, I need, armature current also in the second case. So, you may confuse here, sir. In the previous case, armature current was 10 ampere. Can I take the same armature current in the next case also? No. Remember guys, unless it is given in the problem, you should never assume current is a constant value. Always remember, any parameter you disturb in the machine, current will immediately change. Whether you disturb voltage or whether you disturb flux or whether you disturb torque, power, any parameter you disturb, immediately current will modify. Never assume current is a constant value unless it is given in the problem. Okay, so always assume current changes, any disturbance it is created. Okay, whatever may be the disturbance, current will immediately change. So how to find out the new current? Yes, that is where you have to understand the condition of the load. What was the condition given in the problem? Yes, load torque is proportional to square of the speed. That condition was clearly mentioned. Okay, so it is given that torque is proportional to square of the speed. This is not I am assuming, it is given. At the same time, we know torque is equal to Ka phi into Ia. And here flux is a constant value because machine is separately excited. Therefore, torque is proportional to Ia. This is the equation we know. This is the equation given. Now, if you combine both equations, what is the relation between armature current and speed? Therefore, can I write armature current will be now proportional to square of the speed? Yes, obviously. So, I will continue with this equation. So, Ia1 divided by Ia2 is equal to N1 by N2 whole square. What is armature current in the first case? 10 ampere. What is armature current in the second case? This is the answer we need. And what is the speed in the first case? 1000 rpm. What is the speed in the second case? 500 rpm whole speed. Because we need to reduce the speed to 500 rpm. So if I solve this, I will get new armature current. Okay, so how much it will be? Yes, 500 by 1000 whole square into 10. So I'm getting 2.5 ampere. This is the new armature current. Done. The next thing is calculate the new back EMF. So to calculate new back EMF, I will use a performance equation. What is the back EMF equation? Ka phi into omega. But here flux is a constant value since the machine is separately excited. Therefore, back EMF is directly proportional to speed. So from this, EB1 divided by EB2 is equal to N1 divided by N2. So what is the back EMF in the first case we got? I will go back once. Yes, 90 volt. So 90 divided by back EMF in the second case, this is the value I need, is equal to speed in the first case 1000 RPM, speed in the second case 500 RPM. So the new back EMF is equal to 45 volt. 45 volt. So now I have idea about new back EMF as well as new armature current. Now I will use KVL equation to find out terminal voltage. What is the KVL equation? We know back EMF is always equal to terminal voltage minus IaRa drop, isn't it? What is answer we need? What is the new terminal voltage is the answer. So VT2 is equal to EB2 plus Ia2 into Ra. What is the new back EMF we got? 45 plus what is the new armature current we calculated just in the previous slide? 2.5 ampere. 2.5. And what is the armature resistance given in the problem? I will go back once. Yes, armature resistance is 1 ohm. 1 ohm. So if you complete the calculation, you will get 47.5 volt. So that is the supply voltage required so that 1000 RPM speed reduces to 500 RPM speed. Okay, that's all. Simple question, but only important point is never assume current is going to be same value in the two cases also. Okay, current will always change whenever you create a small disturbance in the machine. Any disturbance it may be. It may be torque disturbance, it may be power disturbance, or it may be flux disturbance, voltage disturbance. Current is a parameter that is subjected to change. How it will change? Will it be doubled, or will it be halved, or will it be 10 times, or becomes 0.1 times? How many times current will change? It depends upon the type of mechanical load connected to the motor. What type of load is connected? Is it a constant torque load, or is it a constant power load, or is it a torque proportional to square of the speed, or torque inversely proportional to speed? What type of load is connected? That will decide the current change. And in this particular question, it is clearly mentioned the fan load torque is proportional to square of the speed. According to that condition, I have to find out what happens to the current. All right. Okay. So let's move to the next question. This is a 1 mark question from GATE 2016 question paper. Read the problem. A 4-pole lap connected separately excited DC motor is drawing a steady current of 40 ampere while running at 600 RPM. A good approximation for the wave shape of the current in an armature conductor of the motor is given by. See, what is the answer we need? A good approximation for the wave shape of the current in an armature conductor. That means we are asked to find out what is the current passing through each conductor of armature. First of all, even though our machine is a DC machine, current passing through each armature conductor will be AC current. Am I right? So that is what you will study in commutation process. Armature current is AC current, but outside the brushes, the line current will be, or armature current will be DC current. Yes or not? And what is the current passing through each conductor? We always know current passing through each conductor is equal to IA divided by A, where A is nothing but number of parallel paths. And what is the total armature current given in the problem? Yes, total armature current is 40 ampere. That is 40 divided by how many parallel paths are there? You see, it is a 4-pole lap connected machine. 4-pole lap connection means 4 parallel paths will be available. Therefore, current passing through each parallel path is going to be 10 ampere. Definitely 10 ampere. And most importantly, it is AC current. output current will be DC current, but inside armature current carried by each armature conductor will be AC current only, that is 10 amperes magnitude. So you can see definitely this is a wrong answer because it is showing DC current. This is also a wrong answer. Now these are the two AC currents, guys. Okay, now how to pick up whether it is sinusoidal current or square wave current? Always remember square wave is the answer. Why? Because in case of DC machine, we are going to use arc shaped pole shoes, right? Suppose if this is the rotor part of the machine, and if I assume two poles, only two pole diagram I am drawing. So every pole will have arc shaped surface, right? Because of this arc shaped surface, air gap remains uniform between stator and rotor. Okay, you can see here the air gap length is uniform. Because of this uniform air gap length, the field flux was distributed in a flat topped manner. Okay, the field flux is distributed in a flat topped manner. Let's say this is north pole field flux, this is south pole field flux with respect to time or space. Okay, so as field flux is distributed in a flat topped manner, obviously the induced voltage is also going to be flat topped voltage, and obviously current passing through conductor will also be a flat topped current. Understand? So that's why flat topped waveform is the correct answer. And the time period will depend upon frequency. What is the formula for frequency? Pn by 120. You can calculate. Actually this is the only square waveform, that's why this is the direct answer. Suppose if I give two square waveforms, one with 50 milliseconds time period, another with some other time period, then how do you calculate time period? Frequency will tell you. Frequency is equal to Pn divided by 120, and in the question 4 poles are there. Machine was rotating at 600 rpm divided by 120. You can see what will be the frequency. 100 hertz. Is it? No, let me calculate it. Yes, I am getting 20 hertz frequency. Frequency is 20 hertz. If frequency is 20 hertz, then what is the time period? 1 by frequency, right? So time period is equal to 1 by frequency, that is 1 by 20. 1 by 20 means, yes, 0.05 seconds, which is 50 milliseconds. Is it the time period? You see first half 25 milliseconds, second half 25 milliseconds, overall time period is 50 milliseconds. Correct, satisfying, right? So it's a square waveform and the time period is 50 milliseconds. Okay, I can give one more waveform, guys. Rather than giving a sinusoidal waveform, let me give you one more square waveform, but a different time period I will use. What is the common time period for 50 hertz frequency? 20 milliseconds, right? So without calculating this, most of the students will select 20 milliseconds as a default answer. But don't do that. Here you have to calculate the frequency, which is 20 hertz. And from the frequency, you have to find out the time period. The time period is 50 milliseconds. Okay. So therefore, current passing through each armature conductor is an AC current, and the shape of the current is a flat topped shape. Understand? Because we are using arc shaped pole shoes. All right. Okay. So we have one more question. This is a question from GATE 2016 paper. A DC shunt generator delivers 45 ampere at a terminal voltage of 220 volt. The armature and shunt field resistances are 0.01 ohm and 44 ohm respectively. The stray losses are 375 watt. What is the percentage efficiency of generator? So first point, it is a generator, guys. As it is a generator, we know for a generator, input power is mechanical power, output power is electrical power. Therefore, we will write efficiency equation in terms of electrical power. Okay, what is the formula for efficiency of any machine? Efficiency is always output power by input power multiplied with 100. Here, who is electrical power? Output power is electrical power. That's why write input power in terms of output power. How can we write? Input power is always equal to output power plus losses. Okay, so our first duty is to calculate output power and then calculate all the losses in the machine. Therefore, we can find out efficiency. What is the formula for output power of a generator? Yes, output power is always equal to Vt into IL. That is the line current delivered to terminals. So what is the terminal voltage given? 220. And what is the current delivered? Yes, this delivered current is nothing but line current 45. So this will give output power. So 220 into 45, 9900 watt. I got output power. Now I have to calculate losses. What are the common losses we will observe in DC machine? Yes, there will be three types of losses. First one is rotational loss. Rotational loss. Second one is armature copper loss. Third one is shunt field copper loss. Okay. And this rotational loss is also known as stray loss in this particular question. That stray loss meaning is nothing but rotational loss plus armature copper loss plus shunt field copper loss. Therefore, to answer the question, first I need to calculate armature current and shunt field current. What is the formula for shunt field current in a shunt generator? Vt by RSH. In the given question, what is Vt? 220, shunt resistance 44. 220 divided by 44, you will get the answer. Yes, 5 ampere. Okay. Therefore, what is armature current? In a shunt generator, we know armature current is equal to line current plus shunt current. Line current is 45, shunt current is 5, overall armature current is 50 ampere, isn't it? Yes. Line current 45 delivered to terminals, and shunt field is 5 ampere, so overall 50 ampere. So calculate all the losses now. Therefore, losses means first stray load loss. How much is given stray load loss? 375. 375. Armature copper loss, that is Ia square into Ra. Ia square into what is Ra value, guys? In the question it was mentioned 0.01, right? 0.01. Shunt field copper loss, Vt into ISH, 220 into 5. So if I complete this, I will get total losses in the machine. Yes, I got 1500 watt. This is the total power loss in the machine. Now I know output power value and also power loss, so I can calculate efficiency. So efficiency is equal to output power divided by output power plus losses into 100. What is output power we got? 9900 divided by 9900 plus 1500 into 100. So yes, the answer is 86.84%. This is going to be the percentage efficiency of the given shunt generator. So you should not confuse about the word called stray loss. Stray loss means generally all other losses except copper losses. Okay, that is indirectly rotational loss in this machine. So we got the percentage efficiency. Got it? So the answer is 86.84. All right, let's move to the next question. This is a question from GATE 2017 paper. So read the problem. A separately excited DC generator supplies 150 ampere to a 145 volt DC grid. The generator is running at 800 RPM. The armature resistance of the generator is 0.1 ohm. If the speed of the generator is increased to 1000 RPM, the current in amperes supplied by the generator to the DC grid. So simple question. First of all, it is a separately excited DC generator. Initially supplying 150 ampere to a 145 volt DC grid. Remember guys, DC grid means indirectly it's a DC bus bar. As it is a bus bar, its voltage will be constant always. Okay. The generator is running at 800 RPM. Now what happened in the next case? The speed is increased to 1000 RPM. What is a new current generated? Okay. So first case machine was rotating at 800 RPM. If speed increases to 1000 RPM, what is a new current generated? Therefore, two cases are involved here. So let's understand case number 1. Yes, machine is connected to a DC grid. That means a terminal voltage is always constant. That is 145 volt, isn't it? I need not to write VT1, VT2 separately because it's a constant voltage. And it is supplying how much current? 150 ampere. Current supplied to grid, that is nothing but line current. But as the machine is separately excited, line current or armature current both are same, which is equal to 150 ampere. And machine was rotating at 800 RPM. So we will calculate generated EMF of this machine. Okay. So what is the formula for generated EMF? Yes. KVL equation. Generated EMF is equal to terminal voltage plus armature current into resistance. Okay. So 145 is the terminal voltage plus armature current is 150. And what is armature resistance given in the problem? 0.1. Okay. So therefore, if you answer this, you will get 160 volt. This is generated EMF of the machine in the first case. But in the second case, what was happened? Speed increases to 1000 RPM. Okay. So case number 2. In case number 2, terminal voltage remains the same. Why? Because machine is connected to bus bar. But now speed is increased to 1000 RPM. We know that whenever speed increases, generated EMF also will increase. What is the formula? Generated EMF is equal to Ka into phi into omega. As the machine is separately excited, flux is a constant value, right? Therefore, Eg is directly proportional to speed. So, Eg1 divided by Eg2 is equal to N1 divided by N2. Okay, so what is generated EMF in the first case? We calculated, yes, 160. 160 divided by Eg2, this is a new generated EMF, is equal to previous speed 800 RPM, the new speed is 1000 RPM. So if I solve it, Eg2 will be equal to 1000 by 800 into 160. Okay, so you will get the magnitude of new generated EMF in volt. Understand? Okay, so the new generated EMF is equal to 200 volt. Okay. Now, once we got new generated EMF, we can easily find out what is the new armature current, isn't it? So, armature current will always flow from Eg to Vt. So, armature current will be equal to Eg minus Vt divided by Ra. Yes or not? As it is second case, use suffix 2. Yes, what is the new generated EMF? 200. Terminal voltage does not change, same 145 divided by armature resistance is 1 ohm. So the answer for new current is 55. Armature resistance is not 1 ohm, it is 0.1 ohm, right? Sorry. Armature resistance is 0.1 ohm. So let me substitute that. If armature resistance is 0.1 ohm, so it will be 55 by 0.1. So the current will be 550 ampere. This is the current generated by the machine when speed was increased to 1000 RPM. Okay. So as the machine is separately excited, flux remains constant. Okay. Easy problem. All right. Let's move to the next problem. This is a question from GATE 2017 paper. It's an objective type question. Read the problem. A 220 volt, 10 kilowatt, 900 RPM separately excited DC motor has an armature resistance of 0.02 ohm. When the motor operates at rated speed and with rated terminal voltage, electromagnetic torque developed by the motor is 70 Newton meter. Electromagnetic torque developed by the motor is 70 Newton meter. Neglecting the rotational losses of the machine, the current drawn by the motor from 220 volt supply is how much? This is the question we need to answer. Okay. So let's try to answer this problem. You see that it is a separately excited DC motor, first point, and the motor is operated at rated speed and also with rated terminal voltage. See, rated speed means 900 RPM, rated voltage means that is 220 volt. Electromagnetic torque is also given. You see that what is the torque developed by the motor? 70 Newton meter. Okay. Neglect rotational losses and what is the current drawn by the motor is the question. So let me note down the data. The voltage at which the motor is supplied, that is equal to 220 volt. The speed at which the motor is rotating, that is equal to 900 RPM. Yes or not? And the torque is equal to 70 Newton meter. Okay. Now, what I can do here is that I can write down the power generated by the machine. That is the mechanical power developed by motor. Motor means input power is electrical, output power is mechanical. Okay, and that mechanical power developed by the machine, you can write two formulas here. One is EB into IA or torque into speed in radian per second. In the question already torque and speed were mentioned, therefore I can directly write down EB into IA is equal to what is the torque? 70 Newton meter, and what is the speed? RPM you convert into radian per second, that is 2 pi n divided by 60. So this will give you the developed power. So if I complete the calculation, 70 into 2 pi n 900 by 60. Yes, this is equal to 6597.34 watt. I will go to the next page. So EB into IA is equal to 6597.34 watt, isn't it? But at the same time, what is EB formula? We all know that EB is equal to VT minus IA RA, as it is a motoring machine, into IA. Yes, into IA. This is equal to 6597.34 watts. Already VT was known, right? What is the terminal voltage of the motor? 220. So what is armature resistance? 0.02. Substitute everything. So 220 minus, we don't know what is armature current, into 0.02 multiplied by IA is equal to 6597.34. So if I multiply 220 IA minus 0.02 IA square is equal to 6597.34. From this, 0.02 IA square minus 220 IA plus 6597.34 is equal to 0. Is it looking like a second order equation? Now if you solve it, you will get two solutions. So please pause the video here and solve this equation, find out the two roots for that IA. Okay, use only gate calculator. All right, I am getting the two roots here. The first choice is 10,969 ampere. This is one possible answer. The second one is 30.07 ampere. Okay, so out of which is going to be the correct answer? How do we decide? Very simple. You take both options and understand which option will give you input power near to output power. What is output power? 6597.34. So if I assume 30.07 as my answer, then what will be the input power? Input power is VT into IL, right? VT is 220, current is 30.07. Remember, it is a separately excited motor, so armature current and line current both are same. So I will get input power, yes, 220 into 30.07. This is 6615.4 watt. See, input power 6615.4, output power 6597.4. So can I say both are very close to each other? And also input power is more than output power. That gap is going to be the losses. Whereas if I select this 10,969 as my answer, the input power becomes way high, very high you will get. Okay, so 220 into 10,969, you will get a huge amount of input power. Definitely that is not going to be the answer. Input power is very high compared to output power, which is not suitable for machine design. Okay, therefore the correct answer will be now, the correct answer will be 30.07 ampere. Okay, so let me go back to the question. What is answer? We need to find what is the current drawn by the motor. Okay, you can also expect 30 is going to be the answer by looking at the options also, because out of the 4 options only 30 is available. In case if it is numerical answer type question, NAT type question, then definitely you have to choose this one as your answer, because this current will give you a much higher input power compared to output power. That shows that machine has too many losses, which is not going to be the practical condition. Okay, yes, therefore the answer is option B, 30 ampere. Okay, all right, let's move to the next question. This is a question from GATE 2017 paper. Very easy question, just to go through it. A 120 volt DC shunt motor takes 2 ampere at no load. It takes 7 ampere on full load while running at 1200 RPM. Armature resistance is given, shunt field resistance is also given. What is the no load speed of the motor is the question. Remember guys, already full load speed is given. You see that? It takes 7 amperes on full load at a speed of 1200 RPM. Therefore, that 1200 RPM is full load speed. We are asked to find out no load speed. So problem is very simple. First take no load condition, calculate back EMF. Next, take full load condition, calculate the new back EMF. Compare both back EMFs, you will get the answer for speed required. So let me take no load data, that is case number 1. Case number 1, no load data. What is the no load data? Yes, the supply voltage was 120 volt. No information in the question that voltage is changing, so I am assuming voltage is constant. And the motor is taking 2 ampere at no load. So the line current at no load, first case, is 2 ampere. Out of that 2 ampere, how much will go to the field circuit, because it is a shunt field, okay, shunt motor. Yes, in shunt motor, field current is equal to Vt by Rf. Vt is 120. How much is the field resistance? 240. Therefore, 0.5 ampere will go to the field circuit, and most important thing is this field current is a constant value. Why field current is constant? Because I am not changing terminal voltage, I am not changing field resistance. That's why field current is a constant value. Then what about armature current? Therefore, armature current is equal to line current 2 ampere minus field current. So 2 minus 0.5, so armature current becomes 1.5 ampere. Okay, now using this, see 1.5 ampere is a very less armature current. Okay, fine. Now using this 1.5 ampere armature current, calculate back EMF of the motor. You solve any number of questions. The moment when a motor question was given, first duty is to calculate back EMF. Okay, so what is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra. So Vt was 120 minus armature current 1.5, and what is armature resistance given in the problem? 0.8 ohm. 0.8. So solving this, you will get back EMF of the motor. Let me do it. 120 minus 1.5 into 0.8, 118.8 volt. That is the back EMF of the motor. This is at no load. Now answer the same question in full load also. In full load, how much current is taken by the machine? 7 ampere. So case number 2. This is a full load case. Okay, so supply voltage does not change, same 120 volt, but current drawn by the motor in the second case is 7 ampere. Out of 7 ampere, field winding is already taking 0.5 ampere. This does not change, right? Field current is constant. Therefore, what happens to armature current in the second case? That is line current minus field current. 7 minus 0.5. So armature current is 6.5 ampere. Using this 6.5 ampere, calculate the new back EMF. What is the new back EMF at full load? EB2 is equal to Vt minus Ia2 into Ra. The terminal voltage is 120 minus armature current 6.5 into armature resistance 0.8. So you will get the new back EMF. 114.8 volt. Now I have a no load back EMF with me and a full load back EMF with me. Find out what is the new speed. What is the formula for back EMF we know? Yes. Back EMF is equal to Ka phi into omega. And here flux is a constant value, guys. Very important. Why flux is a constant value? Because field current is constant. See, first case field current 0.5. Even the second case also field current 0.5. As the field current is constant, definitely flux is also constant. That means back EMF is directly proportional to speed only. So first case back EMF by second case back EMF is equal to first case speed by second case speed. What is answer we need, guys? We need no load speed. That is the first case speed. So what is the back EMF I got in the first case? 118.8. Second case 114.8. Okay. So 118.8 by 114.8 is equal to no load speed is the answer we need divided by full load speed 1200 RPM. So you can easily get the answer for no load speed here. So the answer is 1241.8 RPM. This is going to be the speed of DC shunt motor at no load condition. So if a full load speed is 1200 RPM, no load speed is more than that. The answer is 1241.8. Okay. Alright, let's move to the next question. This is a question from GATE 2018 paper. Okay, read the problem. A separately excited DC motor has an armature resistance of 0.05 ohm. Field excitation is kept constant. This is the important information. At an armature voltage of 100 volt, this is the first case. At an armature voltage of 100 volt, the motor produces 500 Newton meter at 0 speed. The motor produces 500 Newton meter, that is torque, definitely at 0 speed. Neglecting all mechanical losses, the no load speed of the motor in radian per second. We need the answer for no load speed in radian per second for an armature voltage of 150 volt is dash. So here two important conditions are there. First case, machine is supplied from 100 volt. Torque is 500 Newton meter at 0 speed. So let me note down case number 1 details. In the first case, machine is supplied from 100 volt. Okay, torque is equal to 500 Newton meter at how much speed, guys? 0 speed. Okay, 0 speed. If speed is equal to 0, can I say back EMF is also equal to 0? So we know that back EMF is equal to Ka phi into omega. The moment when I said omega is 0, back EMF is also 0. If back EMF is 0, what is the formula for armature current? Armature current will be equal to general formula Vt minus Eb by Ra. Yes or not? But here back EMF is 0, therefore it is simply Vt by Ra. Yes or not? What is Vt? 100. Armature resistance 0.05. Okay, this is equal to 200 amperes, isn't it? Okay, so not 2000, I think 2000 ampere, not 200, it is 2000 ampere. Okay, so let me cross verify. Yes, 2000 ampere. This is the armature current. Now at this armature current, how much torque is developed? 500 Newton meter torque. So what is the formula for torque? We know Ka phi into Ia. Torque is 500 Newton meter. I don't know what is Ka phi value. Current is 2000 ampere. So can you separate Ka phi from here? Yes. Now Ka phi is equal to 500 divided by 2000. That is 0.25. This is the value of Ka phi I got from the first case, and can I use the same Ka phi in the next case also? Yes. Why? Because flux is constant in this motor since motor is separately excited. Now what is the next case? In the next case, motor is excited from 150 volt and also it is at no load. What is the speed? Okay, so let me go to the next case, case number 2. In case number 2, the supply voltage is equal to 150 volt. Most importantly, the machine is at no load. No load condition means armature current drawn by the motor is equal to 0. We know that during no load, the current drawn by the motor is always equal to 0, ideal motor. Okay. If current is equal to 0, what is the speed? Okay, what is the formula for back EMF? We know back EMF is equal to simply Vt minus Ia into Ra. But right now Ia is 0 because there is no load. That means back EMF is simply equal to Vt, which is 150. At the same time, what is the formula for back EMF? Back EMF is also equal to Ka phi into omega. It is a second case, therefore omega 2. Now I need what is the speed in this case, right? What is the speed? Omega 2 will be equal to simply Eb2 by Ka into phi. What is the back EMF I got? 150 divided by what is Ka phi value? Already I identified 0.25. So if I solve it, 150 divided by 0.25, so 600 radian per second. This is the speed I got in the second case. The second case means no load condition with how much voltage? 150 volt. It's a simple question. All right. All right. Let's move to the next question. So after a long time, we got a question from DC series motor. This is a question from GATE 2017 paper. So read the problem. A 220 volt DC series motor drawing a current of 30 ampere from the supply. Armature and field circuit resistances are 0.4 ohm and 0.1 ohm respectively. The load torque varies as the square of the speed. This is important. Load torque is varying as a square of the speed. Okay. the flux in the motor may be taken as being proportional to armature current. To, yes, we know in a series motor, field current and armature current both are same. That's why flux is not only proportional to field current, it is also proportional to armature current. To reduce the speed of the motor by 50%, the resistance that should be inserted in armature circuit is how much? Okay, what is the condition? To reduce the speed of the motor by 50%, what is the resistance to be inserted in armature circuit? Okay, therefore there are two cases here. In the first case, machine was rotating at rated speed. In the second case, I have to reduce the speed by 50%, so that how much extra resistance we have to insert in armature circuit is the question. So first let me note down case number 1 details. Case number 1, what is the terminal voltage? 220, it remains constant, guys. And it is series machine, guys. In series machine, armature current, field current, line current all are same, and that is equal to 30 ampere. Now calculate what is the back EMF of the motor. What is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra plus Rf. So Vt was 220, armature current is 30. Yes, armature resistance is 0.4, field resistance is 0.1. Okay, so this is the information given. So 30 into 0.5, that is 15. 220 minus 15, 205 volt. This is the back EMF of the motor in the first case. Okay. Now coming to the next case, we have to reduce the speed by 50%, guys. And also, what is the condition given? Torque is proportional to square of the speed. So let's move to case number 2. In case number 2, extra resistance is added in armature circuit, right? Is added in armature circuit. We added extra resistance in armature circuit such that speed is reduced by 50%. That means N2 is equal to 0.5 times of N1. And the torque is given. What is given in the question? It is given in the problem that torque is proportional to square of the speed. And we know in series motor, torque is proportional to Ia square. We know that, right? So if I compare both equations, therefore Ia square is directly proportional to N square. That means Ia is proportional to N. From this, first case armature current by second case armature current is equal to N1 by N2. So if I continue, first case armature current 30, we have to calculate what is the second case armature current because we don't know what is a new current. But speed I know, right? Second case speed should be half of the first case speed because we wanted to reduce the speed by 50%. So N1 will cancel. What is the new armature current will become 15 ampere. I told you already, you create any disturbance in a machine, armature current will immediately change. Therefore, never assume the new armature current same as the previous armature current. Always use the condition given in the problem. What is the condition given in this problem? Torque is proportional to square of the speed. Okay. Now using this new armature current, let's calculate what is the new back EMF. Okay. Yes. I have two formulas for back EMF. One is KVL equation, another one is performance equation. So I will first use the performance equation, Ka phi into omega. Therefore, back EMF is directly proportional to, remember guys, this time flux is not constant. It's a series motor. In a series motor, flux is proportional to armature current, right? Armature current into speed. Therefore, EB1 divided by EB2 is equal to Ia1 divided by Ia2 into N1 divided by N2. So what is the back EMF in the first case? We already have 205, right? So 205 divided by EB2 is equal to, what is armature current in the first case? 30, second case 15. N2 is 0.5 times of N1. N1 will cancel. So if I solve it, I will get back EMF in the second case. Let me do that. So I got the new back EMF equal to 51.25 volt. This is the new back EMF I got. But what is the answer we need? What is the extra resistance to be inserted in armature circuit? So by using this new back EMF, write KVL equation so that you can calculate what is the extra resistance added. Okay. So let me go to the next page. So after adding extra resistance, what is a new back EMF? EB2 is equal to VT minus IA2 into RA plus RF. Now extra resistance is also added. Okay. What is a new back EMF we got? 51.25 is equal to what is the terminal voltage, guys? 220, right? 220 minus new armature current 15, armature resistance 0.4, field resistance 0.1. What is the extra resistance? That is the answer I need. So if I solve it, yes, I got extra resistance is equal to 10.75 ohm. You simply solve the above equation, you will get the extra resistance to be added in armature circuit, right? That's all. This is a question from DC series motor. Okay. All right. So we have the next question. This is also from a DC series motor concept. So read the problem. A 200 volt DC series motor, when operating from rated voltage, driving a certain load, draws a 10 ampere current and runs at 1000 RPM. The total series resistance is 1 ohm. Total series resistance means armature resistance plus series field resistance combination. The magnetic circuit is assumed to be linear, that is saturation is neglected. At the same supply voltage means Vt is constant. The load torque is increased by 44%. This is the condition given. The torque increased by 44%. What is the new speed of the motor? We have to answer to the nearest integer. That is the answer we need. So there are two cases here. In the first case, a normal torque is connected. In the second case, torque is increased by 44%. Okay, so let us note down the data. First case 1 details we will note down. What is the terminal voltage? 200 volt. It is a series motor, guys. Therefore, armature current, field current, line current, all are same, right? It's a series motor. How much is the current? 10 ampere. And running at how much speed? 1000 RPM. This is the first case speed. So calculate the back EMF of the motor. What is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra plus Rf. This is what we call it as total series resistance. So Vt was 200. Armature current is 10 ampere. And what is the total series resistance? 1 ohm. Therefore, back EMF is equal to 190 volt. This is the first case. Now in the next case, what was the modification happened? Torque is increased by 44%. So case number 2. In case number 2, the torque is increased by 44%. That means T2 is equal to 1.44 times of T1. Torque increased by 44%. What is the new speed? Is the question. So to find out a new speed, I have to find out a new back EMF. To find out a new back EMF, first I need to find out what is the new armature current, because any disturbance armature current will change. And what is the torque equation we know? We know in a series motor, torque is always proportional to Ia square because saturation is neglected. So from this, T1 by T2 is equal to Ia1 divided by Ia2 whole square. What is T2? T2 is equal to 1.44 times of T1. What is armature current in the first case? 10 ampere. We have to find out armature current in the second case. So T1 will cancel. So find out what is the new armature current from here. Okay. So therefore, if I solve it, so the new armature current will be equal to 12 amperes, isn't it? That is a new armature current. Now using this new armature current, calculate what is the new back EMF of the motor. Okay. So what is the KVL equation we know? The new back EMF is equal to Vt minus Ia2 into Ra plus Rf only. Remember, there was no extra resistance added in the question. So Vt was 200, Ia is 12, total series resistance is 1 ohm. Therefore, this is equal to 208 volt. Once I know what is the new back EMF, I can find out a new speed because we know what is the formula. Performance equation. Back EMF is equal to Ka phi into omega. So from this, Eb is proportional to flux. Remember, flux is not constant. It's a series motor. This is the common mistake majority of the students will do. In a shunt motor, flux is constant. Separately excited motor, flux is constant. But in series motor, flux is proportional to armature current, right? Multiplied by speed. So from this, Eb1 divided by Eb2 is equal to Ia1 divided by Ia2 into N1 divided by N2. Now what is the back EMF in the first case? Yes, 210, right? Back EMF in the first case, sorry, 190. I think I made a mistake. It is not 208, right? 200 minus 12, that is 188 volt, isn't it? Okay, let us substitute. So Eb1 190 divided by 188. Armature current in the first case 10, second case 12. Speed in the first case. What is the speed in the first case? 1000 RPM, right? 1000 RPM. What is the speed in the second case? This is the answer we need. Okay. So you can find out N2 from this particular equation. Okay. So if I cross multiply 188 into 10 into 1000 divided by 190 into 12. So 824.56 RPM. So this is the new speed of the rotor. Okay. So the moment when torque increased by 44%, the speed is reduced to 824.56 RPM. They are asking us to answer nearest integer. Nearest integer means 825 RPM. Okay, that is the answer. Clear? So next question is from GATE 2019. I am not going to solve this question. Why? Because we have a similar question already. I will show you. Yes, same question. See that. A DC shunt motor, no load current was given, full load current was given, full load speed was given. We are asked to find out no load speed. Same model is repeated in GATE 2019 also. Same model, only numbers were modified. Yes, you see that. Now a 220 volt DC shunt motor, 3 amperes no load current, 25 amperes full load current and full load speed was given. What is going to be the no load speed is the question. Okay, same model. I hope you can solve it just like the previous question that we answered. All right. Fine. So we have the next question. This is a question from GATE 2021 paper. 2 marks question. Read the problem. A belt driven DC shunt generator running at 300 RPM delivers 100 kilowatt to a 200 volt DC grid. It continues to run as a motor when the belt breaks. So suddenly the belt broken and the same generating machine started to act like a motor. And now drawing 10 kilowatt from the same DC grid. What is the speed of the motor is the question. Okay. So that means in the first case, the machine is acting like a generator, delivering 100 kilowatt, and then brush is broken. Same machine started to act like a DC motor, but this time drawing 10 kilowatt. Okay. So what you need to do, take case 1, generating case, calculate EG. Next case 2, it is acting like motor, calculate EB, back EMF. Compare both EMFs, you will get what is the speed of the motor. Okay. Same question and same models we are solving many times. Okay. So case number 1 first. In case number 1, machine is acting like a shunt generator. Okay, shunt generator. So what is the terminal voltage first of all? It was connected to a 200 volt DC grid. Grid voltage will never change. Okay. And what is the power it is delivering to grid? 100 kilowatt. And what is the speed at which the machine was rotating? 300 RPM. Now, using this output power, calculate what is the line current. We all know that formula for output power is Vt into IL. That is 100 kilowatt, 10 power 3. So, IL is equal to 100 kilowatt divided by what is the terminal voltage? 200 volt. Okay. So, therefore, the current becomes 500 ampere. Line current 500 ampere. Now, calculate field current also. I will do it here. What is the field current in a shunt generator? Vt by Rf. Vt was 200 by what is the field resistance? 50 ohm, right? 50 ohm. Therefore, 4 ampere will go to field circuit. Okay, line current is 500 ampere. Field current is 4 ampere. Let me check line current again. 10 power 3. Yes, field current is 4 ampere. Therefore, what is armature current? Yes, we know in a shunt generator, armature current is equal to line current plus field current. 500 plus 4, that is 504 ampere. That is armature current. Once I got armature current, I can find out generated EMF. Yes, what is the formula for generated EMF? Vt plus Ia Ra. So Vt was 200, armature current 504. What is armature resistance? Don't forget brush drop is also given, guys. I have to consider brush drop also. Armature resistance 0.025. Normally in questions brush drop will be neglected, but here brush drop is also given. Don't forget that. 0.025. Total brush drop 2 volt, isn't it? Let me go back. Is it brush drop per brush or just brush drop? Just brush drop means total brush drop. Okay, that is 2 volt. So now you combine, you will get generated EMF 200 plus 504 into 0.025 plus 2. So I'm getting 214.6 volt. That is the generated EMF when the machine is acting like a generator. Now belt was broken. Same machine will start acting like a motor. Understand? And drawing how much power? Motor was drawing only 10 kilowatt. It was drawing only 10 kilowatt. So in the next case, the same machine is starting acting like a case number 2 shunt motor. Shunt motor. So terminal voltage does not change because it is bus bar. But this time it is input power 10 kilowatt. So what is the speed of the motor is the question. Yes, what is the formula for input power in motor? Vt into IL, that is equal to 10 kilowatt. So from this IL is equal to 10 kilowatt divided by 200 volt. So the line current is 50 ampere this time. Field current does not change, right? As it is a shunt machine, field current remains constant, which is 4 ampere. Line current was known and field current was known. Now what is armature current? Yes, in a shunt motor, armature current is equal to line current minus field current. That is 50 minus 4, which is equal to 46 ampere. Now calculate back EMF of the motor. What is the formula for back EMF? Vt minus Ia Ra plus brush drop also. So Vt was 200 minus Ia 46 into 0.025. Brush drop is 2 volt given in the problem. So you will get back EMF here. So let me do it. 200 minus 46 into 0.025. Yes, it is 196.85 volt. Now I know generated EMF value and back EMF value. So I can compare both of them to find out the speed. Okay. So what is the formula we know? EMF is equal to Ka phi into omega. Flux is a constant value because in a generating case and a motoring case, same field current was flowing. Okay. Therefore, back EMF is only proportional to speed. So generator EMF by motor EMF is equal to generator speed by motor speed. What is EMF in the generator case? 214.6. Motor case 196.85. 214.6, 196.85. And generator speed is 300 RPM. What is the motor speed is the question. So if you cross multiply, you will get the answer for motor speed. Okay. So the answer will be, yes, I am getting 275 RPM. So that is the speed at which the motor is going to rotate. So when it is acting like a generator, it was rotating at 300 RPM. Now the moment when the prime mover is disconnected, the machine is drawing the power and acting like a motor and rotating at 275 RPM. Easy question. Okay. Okay. So next we have a question from GATE 2023 paper. It's looking like a big question, but the question is very easy. You see that there was a stator and there was a rotor. Stator has 4 conductors, A dash, B dash, and a rotating machine. Okay, the stator part is given, and rotor has 4 conductors A, B, A dash, B dash. What is the voltage induced in these 4 rotor conductors is the question. Rotor was rotating in clockwise direction. So let me redraw the diagram so that it will be easy for us to understand. A, A dash, B, B dash. So first let me draw the stator. This is the stator. So here we have conductor A and here we have A dash. This is conductor B, this is B dash. So indirectly A dash looks like one coil, B dash looks like another coil. A was carrying the current into the plane, A dash was carrying the current out of the plane. B was carrying the current into the plane, B dash was carrying the current out of the plane. Now simply you find out flux direction here. Based on the current direction, we can find out flux direction. I will draw them with a different color. How to find out flux direction? Right hand thumb rule. If thumb represents current direction, the 4 fingers will represent flux direction. See, current is into the plane here. Therefore, my 4 fingers will represent the flux direction. Arrow marks are important. This is how the field flux was flowing. Okay. Similarly, A dash was carrying the current out of the plane. These are the directions of flux lines. Okay. Similarly, this is into the plane. This is the direction of flux line. Okay. So out of the plane. So this is the direction of flux lines. We all know that flux will always flow from which pole to which pole? North pole to south pole in the air medium. So inside the air medium, flux will always flow from north pole to south pole. So according to the arrow mark, you see flux was going this way. That means this area acts like a north pole, and then flux will travel from north pole to south pole. This is south pole. Similarly, this is going to be a north pole. From north to south, the flux was flowing. Okay, so stator has 4 poles indirectly: north, south, north, south. How do you identify the direction of, or you can say polarity of the pole? A simple rule: in the air medium, flux will always flow from north pole to south pole. So according to the arrow mark, I understood. Now coming to the rotor. I will use a different color. I hope it is visible. Now coming to the rotor, I will go back. You see the rotor. I have 4 conductors in rotor: A, B, A dash, B dash. Okay, let me draw them. Now you have the rotor here. There is a conductor A dash, B, B dash. You can check the diagram again. Once again, go back. A, B, A dash, B dash. This is B actually. This is A dash. Okay. So this is B. This is A dash. This is B dash. Now, if you carefully look at these conductors, you see that this is a north pole, guys. You just draw a line passing through this north pole, and you just draw a line passing through the south pole. What is this particular line passing through the pole? We call it as a polar axis. This is nothing but polar axis of the machine. Whichever line is passing through the poles, that is known as a polar axis. But these conductors A, B, A dash, B dash, they are along polar axis or they are intrapolar axis? Yes, the conductors are right now located along intrapolar axis of the machine. Now this red line, yes, this is what we call it as intrapolar axis or quadrature axis. And we know whenever conductors are along the intrapolar axis of the machine, EMF does not induce. Therefore, the magnitude of the voltage in A dash, B dash is equal to 0. No voltage is going to induce in these conductors. Why? Because the conductors are along intrapolar axis. Okay. So if this is a north pole, this is a south pole. In between the 2 poles, there is always interpole. Am I right or not? Intrapolar axis. Okay. This is north pole. This is south pole. Exactly between the 2 poles, there is always intrapolar axis. Similarly, north pole, south pole, the axis between the 2 poles is always intrapolar axis. South pole, north pole, the axis between the 2 poles, intrapolar axis. North pole, south pole, the axis between the two poles, that is interpolar axis. Therefore, according to the diagram, I can understand that all these four conductors A, B, A dash, B dash, they are along the interpolar axis of the machine, also known as magnetically neutral axis. If conductors are along a magnetically neutral axis, the induced EMF is equal to 0. EMF does not induce. That's it. Okay. So what will be the answer? The answer is last option. The induced EMF in both coils A dash, B dash will be equal to 0. So you may assume, sir, it looks like a very big question. It may be a difficult one, but actually this is a very easy question. There are four conductors in stator. Current direction was given. They are just asking you to find out EMF in the rotor conductors, and observation is EMF does not induce in rotor conductors at the moment. Why? Because they are along magnetically neutral axis or interpolar axis. Clear? Okay, so we have the next question. This is also from GATE 2023 paper. Read the problem. A separately excited DC motor rated 400 volt, 15 ampere, 1500 RPM drives a constant torque load. This is the condition given. Drives a constant torque load at rated speed operating from 400 volt DC supply, drawing rated current. Armature resistance is 1.2 ohm. If a supply voltage drops by 10%, see that. If a supply voltage drops by 10%, field current unaltered, then what is the new speed of the motor? So there are two cases again. First case, rated voltage is used. In the second case, voltage was reduced by 10%. Okay, so note down the data. Case 1. Similar models, we solved many questions. In the first case, the voltage was 400 volt. Machine was rotating at rated speed, that is 1500 RPM. Drawing rated current. How much is the current drawn by the motor? 15 amperes, right or not? So calculate back EMF of the motor. Back EMF is equal to Vt minus Ia Ra. So Vt was 400. Armature current was 15. What is the armature resistance of the motor? 1.2. So we will get what is the back EMF of the motor. So let me solve it. 400 minus 15 into 1.2. So 382 volt. This is the back EMF of the motor in the first case. Now in the next case, what was happened? Voltage was reduced by 10%. Voltage was reduced by 10% means the new voltage is 360 because rated voltage 400, guys. If I remove 10%, 360 will be the new voltage. Okay. Now what is the new speed of the motor is the question. But to calculate new speed, first I need a new back EMF. To calculate a new back EMF, I need a new armature current. To find out new armature current, I have to use the condition given in the question. What is the condition? Machine is driving constant torque load. That is the condition given in the problem. Okay. What is the torque equation we know? It is given torque is a constant value according to the problem. But what is the torque equation we know? Ka phi into Ia. Torque is a constant value. It is a separately excited motor. Therefore, flux is also constant. If torque and flux both are constant, indirectly, armature current is also going to be constant. Armature current constant means, can I say new armature current is also same as the previous one? What is the new armature current? 15. Therefore, you can find out new back EMF. What is the formula for new back EMF? Vt minus Ia into Ra. What is the new terminal voltage, guys? 360. Armature current 15. Armature current does not modify. 15. Armature resistance 1.2. So you can find out the new back EMF. Yes, 342. So this is going to be the new back EMF of the motor. So now I have old back EMF and a new back EMF. I can find out the speed. Okay. What is the formula for back EMF? Ka phi into omega. Here flux is constant because machine is separately excited. Back EMF is only proportional to speed. So EB1 divided by EB2 is equal to N1 divided by N2. What is the back EMF in the first case? 382. Second case 362. Speed in the first case. What is the speed in the first case, guys? 1500 RPM. What is the speed in the second case? This is the answer we need. Okay. So find out what is the speed of the motor. So 1500 into 362 divided by 382. So I got 1421.46 RPM. This is the new speed of the motor when supply voltage was reduced by 10%. Okay, very simple question. That's all. These are the questions we have up to GATE 2023 examinations from DC machines, and you can understand after solving all these questions, majority of questions are coming from DC motors only, mainly from shunt motor, series motor, separately excited motors. Okay, so KVL equation, performance equation for back EMF. Okay, most important thing is that you have to focus on whether flux is changing or not, whether armature current is changing or not. If you understand these 2 points, you can answer any question related to DC machine easily. Okay, and we don't have any questions from armature reaction, commutation process of DC machine. Only one question we have, that is what is the current passing through each armature conductor. Is flat topped waveform we got, right? That is the only question we have. But specifically there were no questions from armature reaction and commutation process of the machine. So if you have not yet finished DC machine subject, you can leave those two topics, armature reaction and commutation process. But they are important for other exams like ESE exam, state services exam. They are very important. Okay, but as far as GATE exam is concerned, majority of questions are coming from DC motors only. Okay, right. Thank you so much. So in the next lecture, we will solve previous year examination questions from induction machine subject. Okay, thanks for watching.